simulation from scratch. Therefore, I use a new simulation to create a default device layout. Now I proceed to the definition of geometry for the layer stack of my solar cell. First, I add 4 new layers. Then the first and last layers as a coherent to the surrounding medium, for which I choose air on top and bottom. For these layers, we do not have to specify the thickness. The next layer from the top is the glass substrate, for which a thickness of 1 millimeter is chosen. This is followed by 125 nanometer of ITO as a front electrode, 50 nanometer of P dot, and then 100 nanometer of P3HT PCBM as an active absorber. And I just finish up with a back reflector of aluminum of 100 nanometer thickness. In the first step, the solar cell will be simulated optically with the aim of finding the thickness of absorber layer that produce the maximum short circuit current. For that purpose, we activate the absorption module. Now we have to define the optical property of different layers regarding the material constant and whether the layer is to be treated as a coherent, incoherent, or even as a transport. The glass substrate is treated as an incoherent, not absorbing, which is k equal to 0, and with a constant refractive index n equal to 1.5, that is real part. All the other layer in the stack is coherent, which is default, and the optical constant are imported with proper consideration of the wavelength from NK file in the material database of SETFOS. So we choose here the file import from and then navigate to the proper file. So ITO in this case, same for P dot, import from the database P dot refractive index file, NK file, and then P3HT PCBM NK refract file we will import from database. And finally for the aluminum, since only the absorption in the P3HT PCBM is supposed to lead the photocurrent, internal form efficiency is set to 0 for all the other absorbing layer. So we set here ITO to 0, same for P dot and aluminum. Now I switch to the absorption setting where I can specify the spectrum of the illumination and the wavelength range used to compute the photocurrent generation. For a solar cell under consideration, I choose the air mass 1.5 spectrum between 300 and 900 nanometer wavelength. So after renaming the simulations to OPB optical, I can then run it. So as you can see from the console output, the simulation time is very short for this type of simulations. And I can now proceed the analysis of results from the result test. So this appears after the simulation was completed. First, a look at the key figures. There we can find that the generation current of active layers, which correspond to the optical limit of the short circuit current in the solar cell. We can also have a look at the absorption profile to see where in the device the light is absorbed, and this is to be compared to the generation profile. And we can display these two quantity in the same graph by copying the data and pasting here. In this graph we add some marks to the generations. Finally, you have to quantify the share of different layer in the all absorption, which is displayed in the layer absorptance. So we have here the active absorber layer, absorptance, and the parasitic absorptance of the other layer in the stack. Same information in a slightly different representative can be obtained from the stack contribution plot. Next, we vary the absorber layer thickness in order to maximize the optical generation current. To this end, I activate the sweep mode and insert the parameter of sweep. So in this case, the active layer thickness, which is varied from 50 to 150 nanometer in a step of 5 nanometer. So I can rename here to get the new simulation output and then run the sweep. Now while still very fast, you can see that in order to speed up the simulation in sweep, multi-threading is used. In the result, I can see now the photocurrent as a function of absorber layer thickness, from which I can infer the optimum thickness of around 75 nanometer. The origin of this thickness can also be investigated from the layer absorptance, the active layer. Now as a function of the absorber thickness, and indeed we see that here in this region between 70 and 80 nanometer, we have very broad maximum of absorptance. We now turn to the full optoelectronic simulation of the solar cell. This is we consider the charge transport in addition to the optics. For this purpose, I activate the drift diffusion model in addition to the absorption module. I then have to define the electrode and set the boundary condition for electrical simulations. For simplicity, I use the P dot as anode. So I set here electrode and I use thermionic boundary condition to work function of 4.8 electron volts. And as a cathode, I used aluminum. Again with the thermionic emission boundary condition, but with a work function of 3.9 electron volts. Now the absorber layer in the between is set to the semiconducting. And for this layer, we now have to specify the electrical material properties. And this is again done by importing the corresponding materials file from the database. So I can again check the material database and I will have found here several files which with the material data. So we have here now the constant for HOMO-LUMO levels, effective density of states, dielectric constant, but also the optical generation efficiency, Langmuir recombination efficiency prefactor, and mobility for which a constant model is used. At this stage, we do not consider any excitonic behavior. So we assume that photon absorbs in the active layer generated directly free charge carriers. And for this, we enable in the absorption setting the coupling to charges. Now in order to consider trace and SRH recombination, we have to enable these in the drift diffusion setting, which can also be done here. So if you go again, then go to the activate drift diffusion setting where we have to apply the vice voltage for the simulation. And since we first considered short circuit current conditions, we set 0 as a vice voltage. So we can now rename this. So let's, before we run, we have to deactivate the sweep that we had before. So we only have this only one simulations bias voltage for given configurations. Now in the key figures, we find the short circuit current as the J mean. And the difference to the optical current, which of course is still the same, is informed by the recombination current. And some small leakage component which can be inferred also from the profile of the current that we see here, this leakage. Small leakage parts at the boundaries. Now we can again vary the absorber layer thickness. So I reactivate this sweep here. I run again the simulation. Still very fast simulation. Also, we can now look at the current. We find that the maximum of the short circuit current now appear at a lower absorber layer thickness as compared to the optical simulation, which can now be explained by increase of the recombination current with the absorber layer thickness. Now we should want to have a look at the current voltage characteristics. For that, we replace the sweep over thickness by sweep over voltage from 0 to 750 millivolt with 50 millivolt step size. Now run it. So this provides the current voltage characteristics, the current result plot. If you go now to the key figures, we find all the photovoltaic performance parameters that are inferred from the current voltage characteristics. Open circuit voltage, short circuit current, fill factor, and also the polar conversion efficiency, which in this case is quite low. And so if we go back to the current voltage characteristic, we see that we have quite a lot of recombinations. In order to establish a quantitative relationship between the PV performance and the SRH recombinations, we now vary the density of a defect in additional sweep. We, so we go through the sweep setting and then we add here the sweep, and now look at the electrical materials property. Electronic set here the density of traps from a very low to a rather high value and set one step per decade from a log scale. You can now run again the simulation. So this takes a bit more time as we have to compute JV curve at different defect density, but still it's a quite fast simulation. So now we can have the current voltage characteristics either as individual curve for different defect density, or we can also sweep the JV curve. On the other hand, one can now inspect the photovoltaic performance parameter as a function of defect density. For instance, fill factor, open circuit voltage, short circuit current. From that, one can see that there is a threshold value of about 10 to 11 per cubic centimeter defect density, above which there is a sub-degradation of solar cell performance. For more information, kindly contact on this email ID and mobile number. Thank you.